Hello, and welcome to our deep dive into AP Statistics, Topic 3.14, Chi-square tests for homogeneity and independence. Today, we are going to learn how to set up and justify two powerful tests for categorical data. By the end of this session, you will be able to look at a dataset and determine exactly which chi-square test to use, how to write the hypotheses in context, and how to verify that your results are statistically valid. Let's start by understanding the shape of the math we'll be using. Before we get into the specific tests, we need to talk about the distribution that makes them possible, the chi-square distribution. Our learning objective is to describe chi-square distributions. In previous units, you worked with the normal distribution and the t-distribution, which are symmetric and bell-shaped. The chi-square distribution is quite different. First, chi-square values are always positive. This is because the chi-square statistic is calculated by squaring the differences between observed and expected counts. Since we are squaring numbers, we can't end up with a negative value. The chi-square statistic is the sum of the observed minus expected squared, divided by expected. The chi-square statistic measures the total distance between what we actually saw in our data, the observed counts, and what we would expect to see if the null hypothesis were true. The shape of the distribution depends on the degrees of freedom. When the degrees of freedom are small, the curve is heavily skewed to the right. But notice what happens as the degrees of freedom increase. The distribution becomes less skewed and starts to look more like a normal curve. In our tests for homogeneity and independence, the degrees of freedom will be determined by the number of rows and columns in our data table. Specifically, it is the number of rows minus 1, multiplied by the number of columns minus 1. Keep this visual in mind. As we collect more categories of data, our distribution shifts and stretches. Now that we understand the math behind the distribution, let's focus on one of the most important skills in AP statistics: choosing the right test. When we have a two-way table of categorical data, we are usually looking at either a test for homogeneity or a test for independence. While the math for both is nearly identical, the way we collect the data and the questions we ask are different. Think of the word homogeneous. It means of the same kind. We use the chi-square test for homogeneity when we want to know if the distribution of a single categorical variable is the same across two or more different populations or treatments. For example, do students at North High School have the same distribution of favorite soda brands as students at South High School? Here, we have two distinct populations, North High and South High, and one variable, favorite soda. On the other hand, the chi-square test for independence is used when we have a single population, but we want to see if there is an association between two different categorical variables. For example, if we take a random sample of 200 adults, we might want to know if there is an association between their exercise habits, one variable, and their sleep quality, a second variable. So, the key question to ask yourself is, was the data collected from two or more separate groups to compare them? That is homogeneity. Or was it one group where we measured two different things? That is independence. Once you've identified which test is appropriate, the next step is to state your hypotheses. This is where we define what we are actually testing. Let's start with the chi-square test for homogeneity. Remember, this is used when we compare two or more populations. In plain English, the null hypothesis assumes that everything is the same, that the populations are homogeneous. The alternative hypothesis, HA, states that there is a difference in the distributions of the categorical variable across the populations. Now, let's look at the chi-square test for independence. This is for one population and two variables. The null hypothesis, H0, says there is no association between the two categorical variables in the population, or simply, the two categorical variables are independent. The null hypothesis here claims that knowing the value of one variable gives you no information about the other. The alternative hypothesis, HA, states that there is an association between the two categorical variables in the population. In other words, the two categorical variables are not independent. It is vital to write these in the context of the problem. Instead of just saying the variables, you should name them, like gender and voting preference. Think about the logic here. The null hypothesis is always the boring version where nothing special is happening. No difference, no association, no relationship. The alternative is that there is something interesting going on in the data. Before we can perform these tests, we must ensure the data we have collected is statistically valid. We do this by checking three specific conditions. The first condition is about how the data was gathered. For a test of independence, we need a single random sample from the population. For a test of homogeneity, we need independent random samples from each population, or the data must come from a randomized experiment. This ensures our results are not biased by the way we chose our subjects. The second condition is the 10% condition. If we are sampling without replacement, we need to ensure our sample size, little n, is less than 10% of the total population size, big N. This allows us to treat the individual observations as independent. However, if your data comes from a randomized experiment rather than a sample of an existing population, you do not need to check this condition. The third condition is the expected counts condition. This is the most common place where students make mistakes. All expected counts must be greater than or equal to 5. Note that this refers to expected counts, not the observed counts you see in the table. You must calculate the expected values for every cell in your table and verify that every single one is at least 5. If some are too small, the chi-square distribution might not be a good model for our data. To calculate the expected count for any cell, take the row total multiplied by the column total and divide by the grand total. In a moment, we will look at an example to see how to calculate these and verify the conditions in a real scenario. Let's apply everything we've learned to a practical example. This will help you distinguish between the two types of tests in a real-world context. A researcher wants to know if there is a relationship between the type of music a student listens to while studying and their GPA category. They take a random sample of 300 students from a large university and record both their preferred music genre and their GPA. The data is organized into rows for music types like classical, rock, pop, or none, and columns for GPA categories. The grand total is 300 students. First, which test should we use? Take a moment to think. Is this multiple populations being compared, or one population with two variables? The researcher took a single random sample of 300 students. Then, they measured two categorical variables for each student, music genre and GPA category. Because it is a single sample with two variables, we are checking for an association. The appropriate test is the chi-square test for independence. Now, let's write the hypothesis in context. The null hypothesis, H0, states, there is no association between preferred music genre and GPA category for students at this university. The alternative hypothesis, HA, states, there is an association between preferred music genre and GPA category for students at this university. Next, we must justify the use of this test by checking the conditions. 1. Random. The problem states a random sample of 300 students was taken. 2. 10%. 300 is likely less than 10% of all students at a large university. 3. Expected counts. We would need to calculate these. If all are 5 or greater, the condition is met. Remember, we don't just list the conditions. We must state why they are met using the information provided in the problem. This in-context justification is what AP graders are looking for. Now, let's look at a different scenario to see how the setup changes. A nutritionist wants to determine if the distribution of lunch choices is the same for elementary, middle, and high school students. They take independent random samples of 100 students from each school level and record whether they chose a hot meal, a sandwich, or a salad. Here is our two-way table with school levels as rows and lunch choices as columns. Which test is appropriate here? Notice that the researcher didn't just take one big group of students. They took 3 separate independent random samples, one from each population of school levels. They are comparing the distribution of a single variable, lunch choice, across those 3 populations. The appropriate test is the chi-square test for homogeneity. Because we are looking for a difference between groups, our hypotheses will look like this. The null hypothesis states there is no difference in the distribution of lunch choices across the 3 school levels. And the alternative hypothesis states there is a difference in the distribution of lunch choices across the 3 school levels. Let's check the conditions for this specific case. First, the random condition. The problem states independent random samples were taken from each school level. Notice the phrasing there. It's important to mention that there are multiple samples. Second, the 10% condition. It is reasonable to assume that 100 students is less than 10% of all elementary, middle, and high school students respectively in a large district. Third, the expected counts condition. We calculate the expected count for each cell. For example, if 150 students total chose a hot meal, the expected count for elementary students choosing a hot meal would be 100 times 150 divided by the total of 300. Since 50 is greater than 5, this specific cell passes. We would repeat this for all 9 cells in the table. If all are 5 or higher, we are ready to calculate our chi-square statistic. Let's dig a little deeper into the expected counts condition, as this is where the most calculation happens when setting up these tests. Recall our formula for the expected count of any cell in a two-way table. Why do we do this? This formula calculates what the count should be if the null hypothesis were true, meaning if there were absolutely no relationship between the variables. Let's look at this small table comparing coffee and tea preferences. To find the expected count of teachers who prefer coffee, we look at the row total for teachers, which is 50, and the column total for coffee, which is 70. Expected teachers' coffee is 50 times 70 divided by 100. 3,500 divided by 100 is 35. The observed count was 40, but if the null hypothesis were true, we would expect only 35. In this case, all our expected counts are 35 or 15. Since both of those values are greater than or equal to 5, our expected counts condition is met. Even if the observed data has a 0 in a cell, the test might still be valid as long as the expected count for that cell is 5 or more. Never look at the raw data to check this condition. Always calculate the expected values first. If you find that an expected count is less than 5, you cannot proceed with a chi-square test. In a real study, you might have to combine categories to increase the counts or collect more data. To ensure we hit our target length, let's take a comprehensive look at a complex scenario that often appears on exams. We'll walk through every step from identification to condition checking. A medical researcher is studying the effectiveness of 3 different treatments for a specific condition. They randomly assign 90 patients to one of 3 groups: treatment A, treatment B, or a placebo. After 6 months, they record whether each patient's condition improved, stayed the same, or worsened. Let's break this down. Is this homogeneity or independence? This is a randomized experiment with 3 different treatment groups. We are comparing the distribution of the outcome variable across these 3 experimental groups. The appropriate test is the chi-square test for homogeneity. Whenever you see randomized experiment or assigned to treatments, lean toward homogeneity. Now, let's state our hypotheses carefully. The null hypothesis is, there is no difference in the distribution of outcomes across the 3 treatment types. The alternative hypothesis is, there is a difference in the distribution of outcomes across the 3 treatment types. Now for the conditions. Pay close attention to how we phrase the justification. 1. Randomization. Condition. Met. The problem states that patients were randomly assigned to the 3 treatment groups. 2. 10% condition. Not necessary. Remember, because this is a randomized experiment and not a sample from a larger population without replacement, the 10% condition does not apply. 3. Expected counts. We must calculate all cells. Since we have 3 rows and 3 columns, there are 9 expected counts to check. If we assume the outcomes were split evenly, each row total is 30. If 30 people total improved, the expected count for treatment A and improved would be 30 times 30 divided by 90, which is 10. Since 10 is greater than 5, this cell is safe. We would perform this for every cell in the 3x3 table. If all 9 results are 5 or greater, we have successfully justified our test. Take a second to think about what a difference in distribution would actually mean here. It would mean that at least one of the treatments, say treatment A, had a significantly higher proportion of improved patients than the others. That's exactly what a researcher wants to find. It is also helpful to understand what the chi-square statistic actually represents visually. Let's look at the distance we mentioned earlier. When we calculate the statistic, we are doing a cell-by-cell comparison. Each cell in your table contributes to the final chi-square value. If the observed count is very close to the expected count, that cell's contribution is near 0. If they are very different, the contribution is large. The larger the final chi-square statistic, the more evidence we have against the null hypothesis. On our distribution curve, a very large chi-square value will fall far into the right tail. This results in a very small p-value. If the p-value is smaller than our significance level, usually 0.05, we conclude that the differences we see in the data are too large to be explained by random chance alone. Think about it. If the null hypothesis of homogeneity is true, we expect the proportions to be almost identical across all groups. Any variation we see should be small. But if we see a massive difference in one category, our chi-square statistic will blow up, pushing us toward the conclusion that a real difference exists in the population. This logic is the same for both independence and homogeneity. The only thing that changes is whether we are concluding there is an association or a difference in distributions. Let's look at one final example that often trips students up, because it deals with a survey design. A market research firm wants to know if age group is related to the primary device used for internet browsing. They select a single random sample of 500 adults and record their age group and their primary device. First, identify the test. Even though we are looking at different groups of ages, the key is how the data was collected. The firm took a single random sample of 500 people and then categorized them. We use independence because we are looking for a relationship between two variables, age and device, within one population. If they had sampled 100 young adults, 100 middle-aged people, and 100 seniors separately, it would have been homogeneity. Do you see the subtle difference? Now, let's write the hypotheses. Next, we justify. 1. Random, met. A single random sample of 500 adults was taken. 2. 10%, met. 500 adults is definitely less than 10% of all adults in the population. 3. Expected counts. We check if the row total times column total divided by 500 is at least 5 for all 9 categories. Finally, we need to determine the degrees of freedom for this table. Since we have 3 rows and 3 columns, the degrees of freedom is 2 times 2, which equals 4. With 4 degrees of freedom, we would look at a chi-square distribution with df equals 4 to find our p-value. Notice that with 4 degrees of freedom, the peak of the curve has shifted slightly to the right, compared to a curve with only 1 or 2 degrees of freedom. This is the family of curves we discussed earlier. To wrap up, let's summarize the key takeaways from this lesson on chi-square tests for two-way tables. First, remember that chi-square distributions are always positive and right-skewed. As your degrees of freedom increase, the skewness decreases. When choosing your test, look closely at the sampling method. If you see multiple independent samples or experimental groups, choose homogeneity. If you see one single random sample where 2 pieces of information were recorded for each subject, choose independence. The null hypothesis, H0, usually states there is no difference or that variables are independent. The alternative hypothesis, HA, states there is a difference or they are not independent. And finally, never forget your justifications. Use the 3-step check: randomization, the 10% condition for samples, and ensuring all expected counts are at least 5. If you follow these steps carefully, you will be able to set up any chi-square problem with confidence. We have now described chi-square curves, distinguished between test types, formulated hypotheses in context, and verified all necessary conditions. We have now covered the essential knowledge for topic 3.14. Take some time to practice these setups with different datasets to sharpen your intuition for the sampling methods. Thank you for watching. Good luck with your AP Statistics studies. Great work today. You are now ready to tackle chi-square inference with precision and clarity.